Hello, in this video I want to answer as best I can what is the Michael addition. It's still part of enolate chemistry. We've had the aldol, we have the Claisen, and now we have the Michael. So if you think about the reactions in the enolate portion of your textbook, we have the aldol and obviously the aldol condensation. We have the Claisen. Technically it is a condensation, but I just call it the Claisen reaction, or just Claisen. And then we have what's called the Michael addition. To recognize the Michael addition, you need two things. You need a molecule that can form the enolate. So you need partner A will be the enolate. So stuff like this, aldehydes. But don't forget, you could also have, diesters or diketones. So here, let me draw your diester. Right, how do you form the enolate? You deprotonate the alpha carbon. So both of these have a very good alpha carbon, an alpha carbon where you could strip off the hydrogen. There are other enolate forming molecules that you may be familiar with, but I'm not going to put them here. And for my class, you really just have to worry about the aldehydes, ketones, and esters, and the di stuff, the diketones, the diesters, the dialdehydes. So basically, stuff that looks like this, or molecules that look like that. And you need what's called a, how do I say this? Plus a, I call it a conjugated enone. If I think of a better name, I'll let you know. Enone for alkene ketone, but it could also be an alkene aldehyde. So stuff like, and I just put here, etc. Okay, stuff like this. The simplest would be this molecule here. See if you could spot a pattern. That's one conjugated enone. Another possibility could be this. Okay, see how the double bonds are conjugated to each other? Double bond, single bond, double bond. And so right now that's the best name I could think of. And you could have other stuff like, heck, you could even have, or this is, sometimes they'll make it an amide. Okay, it's still going to operate like the other two. So those are your two ingredients. Okay, the one green and one blue. You're going to run it under base, right, to get the enolate. So some type of base like NaOH or NaOET. Let me change the color. What color have I not used yet? Okay. Let me give you an example, and then we'll go over the mechanism. Before I do that, this conjugated enone molecule has very unique properties where if you number from the oxygen all the four atoms that are sp2, 1, 2, 3, and 4, 1, 2, 3, and 4, 1, 2, 3, and 4, for the Michael addition, you attack the 4 position. So the Michael, and we'll see in the mechanism why this is the case, the Michael addition is a type of, it's called 1,4 addition. Now, I already told you that maybe I didn't explicitly say this, but the bond that will be made will be between the alpha and the 4. And so if you want, we are going to get something on oxygen, but it won't show up in the final product. It will show up in the mechanism. And that's why we call it 1,4. 4 gets this stuff, oxygen gets a hydrogen, but in the mechanism we're going to lose it again, so you don't see it. You won't see it in the final product. That's called 1,4 addition. The additions on a carbonyl that you've learned in the past have always been what's called 1,2. Remember Grignard. Grignard attacks here, you make it an alcohol. That's 1 and 2. Each atom, 1 and 2, gets something. There are other examples, like when you do acetal formation, right? You have an alcohol attack. It always attacks the carbonyl group, right? And you always, for the hemiacetal, you make the OH. So Michael is very unique in the sense that you're not attacking here anymore. You are attacking here. Now, I won't get into why some nucleophiles attack here, like the enolates, and some nucleophiles attack here, like the Grignard. That is a topic that is not too important yet to understand the main points of the Michael. Okay? So I introduced the word nucleophile, right? So we'll be the enolate nucleophile. Okay. Let me give you an example, and then let me draw the product. Okay? And then the mechanism. So let's take this possible enolate. Okay, let's not do that. Let's still have the ring, but let's not make it benzene. Let's be very clear that this is. Oh boy. Okay, so let me put a methyl group here so there's no ambiguity. I only want us to use this alpha carbon, okay? And then for the Michael partner, we'll make. Let's start simple at first. Let's use this. The simplest. Well, I'll put a methyl group. One of the simplest enones that we'll have. Next, we have a base. It could be any base, any oxide base. Is that true? It could also be LDA, because we're not doing a self-aldol. Okay, we're doing a Michael. But this is fine. Let's give us a protic solvent. Okay, so here's the deal. Your numbering was this. 1, 2, 3, 4. I told you that Michael is the type of 1,4 addition. So you're going to draw the attacker as is. And you're going to make the new bond between the alpha and not the carbonyl carbon. Remember how I used to put a dot here? Well, not this time. The dot is going to go here. So that 4 position is right here. And guess what? For the final product, you just draw everything. Leave out the carbon-carbon double bond. And if you need to verify, this is, again, 1, 2, 3, and 4. So it's obvious that we added something on 4. So we have something on it at 4 addition. Why is it called 1 addition? Or why is it called 1,4 addition? Before we look at the mechanism to see where the 1,4 addition comes into play, this is your product, okay? And so what is it typically? It's typically if you count carbons this way, you have 2 carbonyls that are 5 atoms apart. So 1, 2, 3, 4, 5. You get a 1,5 dicarbonyl. Whenever you do a Michael, that's what you should be getting, a 1,5 dicarbonyl. Okay, whether it's an aldehyde, depends whether this is an H. Whether it's an ester, it depends whether this is an ester. Okay, but it's dicarbonyl, 1 and 5. Okay, the mechanism. We're going to form the enolate first. What colors do I want to use? I put a methyl group here because I don't want us to use the alpha carbon on the left. I only want us to use one alpha carbon, and this it's the one on the right. We have base, and here's your first arrow, second arrow, third arrow. So yes, this is part of the enolate chapter. We are making an enolate. Now we could use LDA. I think I'll write that also. In the previous video, I talked a little bit about LDA. I mean, I think I talked a lot about LDA, and I was very explicit on what you need to know about LDA and how to fill in the products if you use LDA. But you could also use LDA here because it doesn't matter that we convert this molecule 100% to our enolate, which I haven't drawn yet. Here, enolate. One more. Okay, there. It's okay to have 100% of this because we're not attacking another one of itself. We are doing what? We are attacking now the conjugated enone. So here it is. So check this out. You remake the double bond, so I need my lone pairs for sure. You remake the double bond, just like with a regular aldol, and you attack the... Oops. I said regular aldol, and I almost attacked the carbonyl. I should be attacking carbon number 4, not carbon number 2. So I caught myself. So the double bond forms like an aldol, but now we're going to attack right there. We attack right there because that carbon has partial positive character due to resonance. But anyway, we attack, we shift this over, and we get this to be O minus. So we're not at the product yet, right? We're not at the product yet. Actually, we might be at least 2 steps away. Let's just see. I'll stop writing CH3, I'll just put a line. And I am confused now. 1, 2, 3, and 4. So this is the alpha. So I think what people sometimes do is they draw this. You don't draw this. But if that's really the alpha, are you telling me that this is the 4 position? That doesn't make any sense, right? The 4 position is several carbons away from the oxygen. Okay, so that's wrong. So I think maybe what people are saying is that maybe this is alpha and carbon number 4. That's impossible, right? You have to make a new bond between alpha and 4. It can't be the same carbon. Okay, so obviously I'm missing a lot of carbons. Here's your alpha. And you're going to make a new bond to carbon number 4. It just turns out the zigzag works out perfectly. 4 up, 3 down, 2 up, oxygen minus. Okay, your double bond has shifted and you're now here. Okay. We're almost done. We have ETOH. Okay, so what you could do is you could remake this double bond and attack that hydrogen. What could also happen is that the oxygen can be protonated, but I'm not going to do that in the mechanism. So at this point, I'm going to say something like this. Carbon 4 was attacked. Atom 1 is negative now. Okay. I'm going to call this, the reason why we call this a 1,4 addition. And I set that up here, right? the Michael is considered a 1,4. So either you think of this as later protonated, but in my mechanism it's not protonated. Or you think of it, 4 got the nucleophile, 1 got the charge. Either way, we call this 1,4 addition. Okay, not the final product. Not the final product. The final product is this. We make the double bond. We have this protic solvent available. And then go ahead and grab... Remember where your alpha is, by the way? Your alpha is here, okay? But for this enolate, okay, we're attaching the hydrogen here. So we have that, and boom, boom. That will give us our final product. Practice your Michael addition mechanism. But you know there's a shortcut to draw the product. Right? What's the shortcut? Find the alpha connected to atom number 4. 4, 3, 2, 1. The bond that you made was this bond right here. So look how similar, by the way, the parts of the final product look like the starting material. This is drawn exactly. And then this piece you added, the only thing you have to do is get rid of the carbon-carbon double bond. Everything else stays the same. We also know that if you form a 1,5-dicarbonyl, you did the Michael addition correctly, or drew the product correctly, and yes, we have 1,5. So this is a 1,5 diketone, or just say dicarbonyl. The Michael addition for my class is 3 steps, 1, 2, 3, and you will get 2 carbonyl groups on the molecule. Okay, that is the Michael addition. Now, imagine instead of this as becoming the enolate, imagine this becoming the enolate. It's the same deal. You're just connecting alpha to the 4 position. Okay, put angles and make sure your bonds are straight. Okay, I don't want any curvy bonds just because you were maybe a little bit misaligned. Okay, or you're too far away and you're trying to draw something like this. Okay, that's a curved bond right there. Okay, make it straight if you want to do something like that. Okay, that is basically all I need people in my class to know for the Michael addition. Predict the products and draw the mechanism. The mechanism is going to be, for me, 3 steps.